In this video, we will learn about the derivatives of vector-valued functions. So all our single variable differentiation techniques are going to come back now in the form of a vector function. So to start, the derivative r prime of t of a vector function r of t is defined as dr dt, or r prime of t as far as our notation goes, and it's equal to the limit as h approaches 0 of r of t plus h minus r of t over h. So essentially, we are subtracting two vectors, r of t plus h minus r of t, and if we take the limit as h approaches 0, what we're going to be left with is our derivative vector, r prime of t. The derivative of a vector function is equivalent to taking the derivative of each component function as long as each component is continuous. All right, so we need continuity among the component functions in order to differentiate. So if r of t equals f of t, g of t, h of t, so those are the three component functions, then r prime of t is going to be equal to the derivative of each of those components. So f prime of t, g prime of t, h prime of t. So first example, find the derivative of r of t equals 2t over t minus 5, square root of 2t minus 1, natural log of 3t. So we have a few different differentiation techniques that are going to come up in this example. So r prime of t equals, in order to differentiate the first component function, we're going to need the quotient rule. Recall that's bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared. Okay, so bottom times the derivative of the top times 2 minus the top times the derivative of the bottom is 1 all over the bottom squared, so t minus 5 squared. Differentiating the second component function, square root of 2t minus 1, I'm going to express that as 2t minus 1 to the 1/2, and we'll use the chain rule here, so 1/2 inside stays the same, so 2t minus 1 to the negative 1/2, right? So power rule, times the derivative of the inner function, which is 2. And then we have the derivative of a natural log function, so that's 1 over the inner function, so 3t. And again, chain rule here, derivative of the inner function, which is 3. So now we can simplify, just so we have a nice derivative vector. So r prime of t then would be equal to, so we're going to have 2t minus 10 minus 2t, so that's just going to be negative 10 over t minus 5 squared. And write out that simplification. I just tried to talk through it. Now here the 1/2 times the 2 is 1. The negative exponent will move that down to the denominator, and I'll put it back as a square root, so this 1 over the square root of 2t minus 1. And then the 3 and the denominator simplify, so that's just 1 over t. So our derivative vector, r prime of t, is negative 10 over t minus 5 squared, 1 over the square root of 2t minus 1, and 1 over t. So the next piece we're going to talk about is a vector function being smooth. So a vector function r of t is smooth if r prime of t is continuous and non-zero on an interval I, which is just some preset interval. Maybe it's 0 less than or equal to t less than or equal to 1. Maybe it's 0 less than or equal to t less than or equal to 2 pi. Maybe t can be any real number, right? Whatever it is specified for the problem. So what it means to be smooth, if we draw a few examples, right? So this is an example of a space curve that would be smooth, right? This is a smooth vector function. Here, if we drew like a cusp, right, this would be not smooth. So let's label this one as smooth. Okay. Each piece here, if we divided it into two pieces, it would be two smooth pieces, or piecewise smooth, but as one curve, it would not be smooth because r prime of t is not going to be continuous. R prime of t at that cusp is not going to exist. And then you could have a break in the space curve, right? So maybe it goes like that, right? That would be another example of a space curve that is not smooth. So This definition really just allows us to use the word smooth when we are talking about having continuous derivatives, right? Component functions whose derivatives are also continuous. And that just makes it easier for us to define when we are referring to a theorem or a result that we need r prime to be continuous. We can now just use the word smooth, a little bit more concise. Evaluating r prime of t at a specific value of t gives a tangent vector to the curve at the point provided r prime of t exists and is non-zero. So single variable calculus, we have a lot of discussions about tangent lines. Now with vector functions, we're talking about tangent vectors. So r prime of t will give us a tangent vector to the curve at whatever point we're evaluating r prime of t at. So consider point P defined on the curve C by r of a. The tangent line to the curve C at a point P is the line whose direction vector is parallel to r prime of a through the point P. Now, with all the letters, that can be a little bit confusing. What this is saying is if we want to write a tangent line to a vector function, we're going to use r prime at whatever point we're writing the line as our direction vector. Okay, because the direction vector is going to be parallel to the tangent vector at that point. Right? That's all this is saying. We'd write the line the same way, whether it be as a vector function, as parametric equations, the same way that we've done previously. But now the derivative vector, r prime, is going to give us our direction vector for that line. And then the unit tangent vector, we've had a lot of discussions about unit vectors, vectors whose magnitude are 1. So the unit tangent vector gets its own notation, capital T of t, and that's going to be defined as r prime of t, the tangent vector, over its magnitude, r prime of t, since that's how we create a unit vector. Take a vector, divide it by its magnitude, we've created a vector in the same direction, but of magnitude 1. Right? But in this case, it gets its own notation. So if we see capital T of t, that is referring to the unit tangent vector. And this is how we would find it. Sometimes we're going to find it in terms of t. Sometimes they'll ask us to find it at a specific point. Regardless of where they're asking you to find it, this is how we're going to do so. So consider the vector function r of t being equal to t times e to the t squared plus 4, 3t. So part A, find a vector equation for the tangent line to the curve at the point 0, 4, 0. Okay, so in order to write a line, just in general in 3 space, we need a point and we need a direction vector. Direction vector. Okay, so we have the point covered. They give us the point 0, 4, 0. We need a direction vector, which in this case, we're going to use r prime at whatever t value the point's defined at. So let's start by finding r prime of t, our derivative or our tangent vector. So the derivative of the first component is going to require the product rule. So that's going to be first times the derivative of the second, which is just e to the t, plus derivative of the second is 1, derivative of the first rather is 1 times the second, which is e to the t. The derivative of the second component function, t squared plus 4, will just be 2t, power rule. And then derivative of 3t will be 3. Now we want to evaluate this derivative at the point 0, 4, 0. The issue is r prime of t is defined in terms of t. So we can only plug in a single value to get our tangent vector. Whereas the point 0, 4, 0 is defined in terms of an x, a y, and a z. So we need to use the original function r of t to figure out what value of t generates the point 0, 4, 0. Right? So essentially we're saying t e to the t equals 0, t squared plus 4 equals 4, and 3t equals 0. What t value makes all 3 of these equations true? So hopefully we can all agree pretty easily that that's going to be t equals 0. That would be 0, this would be 4, this would be 0. So we're now going to evaluate r prime at 0 So that's going to be 0 plus 1, so 1, 0, 3. So this is going to be our direction vector. So our direction vector is 1, 0, 3. We have our point 0, 4, 0. So the equation of the line is going to be x equals 0 plus t, y equals 4 plus 0t, z equals 0 plus 3t. Are the zeros all necessary? No. Most likely you're just going to write this as x equals t, y equals 4, z equals 3t. But just as a reminder of what the different components of writing a line look like, right? And then it says vector equation, so I wasn't paying attention. So really what your answer should look like is r of t equals t 4, 3t, right? I had written them parametrically. We take those parametric equations and write our vector function for the line. So then part B, find the unit tangent vector when t equals 0. So we are looking to use our new notation for capital T of 0. Well, that's going to be r prime of 0 over the magnitude of r prime of 0. We already know what r prime of 0 is, so we don't have to do any new computation. So r prime of 0 is equal to 1, 0, 3. The magnitude of r prime of 0, square root of 1 squared plus 0 squared plus 3 squared. So the magnitude of r prime of 0 is equal to the square root of 10. So then our unit tangent vector is going to be 1 over the square root of 10 times the vector 1, 0, 3. And if we want to distribute that out, the unit tangent vector at 0 will be 1 over the square root of 10, 0, 3 over the square root of 10. Okay, so that's our tangent vector that has a magnitude of 1. Now talking about our differentiation rules as they apply to vector functions. They'll mostly follow from our single variable differentiation rules, but we're just going to write them out with vector functions now. So if we're taking the derivative with respect to t of the sum of u of t and v of t, then our derivative is going to be u prime of t plus v prime of t. So we just differentiate the vector function u and add it to the derivative of vector function v. Now, if we are taking the derivative with respect to t of c times u of t, so c is just some scalar. We can write that up here. So c equals a scalar, just a number. So then it's going to be c times u prime of t. So a scalar is not going to affect the derivative of the vector function. Now if we're going to take the derivative with respect to t of f of t times u of t. So f of t is a scalar function now, right? Maybe it's t squared, to give an example. And then u of t is some vector function. The derivative is going to require the product rule. So derivative of the first times the vector function u of t, and then plus that scalar function f of t times the derivative of the vector function u prime of t. Okay, so like I said, vector, the scalar function could be t squared, would be a great example, 3t. And then you have a vector function, maybe it's the vector t squared, t cubed. Right, so we're taking the derivatives of both of those using the product rule. Now if we're taking the derivative with respect to t of a dot product, same thing, product rule. So u prime of t dotted with v of t, so derivative of the first times the second, where in this case the multiplication is defined by the dot product, plus the first dotted with the derivative of the second, v prime of t. Fifth one, derivative with respect to t of now a cross product, same idea. So product rule, so u prime of t crossed with v of t plus u of t crossed with v prime of t. Now out of the three product rules, the order matters in the third one. right? So all of these are really just examples of the product rule. And this last one, the order matters as far as the cross products go. Because remember, U cross V is different than V cross U. So when we go to expand with the product rule, it's important that U always stays first, V stays second in each cross product, and then you add the appropriate derivative, right? So differentiate U, differentiate V, but still U and V in relation to one another, U always comes first in this cross product. And then 6, if we take the derivative with respect to t of U of f of t, so now we have a composition, scalar function inside of a vector function, we use the same chain rule. So derivative of the vector function, the scalar function stays the same, and then times the derivative of that scalar function. Okay, so there are the differentiation rules just apply to vector functions, or written out with vector functions now. The nice part is they're the same. We still have a product rule, we still have a chain rule, we multiply by a scalar, or we have vector addition, we're able to differentiate without much issue. So given r of t equals t cubed 5 2t, and f of t equals 1 over t squared, find the derivative with respect to t of f of t times r of t using the product rule. Okay, we don't need that equal sign there, but it doesn't hurt. Okay, so what we're going to do, derivative with respect to t of f of t times the vector function r of t. Right, so that's going to be a product rule. So it's going to be f prime of t times r of t plus that scalar function f of t times r prime of t. So we just need to find each of those quantities and then simplify. So f prime of t would be the derivative of 1 over t squared. I'm going to think of that as t to the negative second. So that's going to be negative 2 t to the negative third. And then r of t is the vector function t cubed 5 2t. And then plus the scalar function 1 over t squared. And then the derivative of r of t now, so 3t squared, 0, 2. And then if we want to combine to get a single vector quantity, so we can distribute. So first think of this as negative 2 over t cubed. So we're going to have negative 2, negative 10 over t cubed, negative 4 over t squared, plus 3, 0, 2 over t squared. And the nice part is we can combine this without much effort. So that derivative then is equal to 1, negative 10 over t cubed, and negative 2 over t squared. Okay. So our last example for this video showed that if the magnitude of r of t equals c, which is some constant, pick a number, then r prime of t is orthogonal to r of t for all t. So essentially what this is saying is if we have a vector function whose magnitude is always a constant, regardless of what value of t you plug in, the length of that vector is always going to be the same. So a circle would be an example of this, right? Plug in any value, the vector function or the vector you're going to get is going to be, or the magnitude of that vector would be the radius, right? It's going to be constant as you go along that circle. So what we're trying to show in that case is the tangent vector orthogonal to the original position vector, okay? So the key here to unlock this problem is using one of the properties of the dot product, which is if we square the magnitude, so we'll square both sides, the magnitude of a vector function squared is equivalent to the dot product of the vector function with itself. And by doing this, now we can differentiate both sides with respect to t. Right, so this was just relying on a property from the dot product. Now we can differentiate. We'll use the product rule on the left side. So r of t, or r prime of t, dotted with r of t, plus r of t, dotted with r prime of t. And then the derivative of c squared is just going to be 0. It's a constant. Derivative of a constant with respect to t is going to be 0. Now here we have two expressions that look similar except the order is different. But remember, for the dot product, the order does not matter. So this first one is the same as saying r of t dotted with r prime of t, since the order doesn't matter, which means we really have two r of t dot r prime of t's equaling 0. If we divide both sides by 2, we really have r of t dotted with r prime of t equals 0. And again, back to those properties of the dot product, what does it mean if we have two vectors or vector functions whose dot product is 0? Well, what that tells us is that r of t is perpendicular or orthogonal to r prime of t, which is exactly what we wanted to show, right? We want to show that r prime of t is orthogonal to r of t. And again, to visualize this example, an example of this would be a circle. If you have a circle, the position vector, I can draw a circle. What we're trying to show is, okay, all of these r of t's are going to have a constant length. They're all the radius. And we're trying to show that in this case, r prime of t is orthogonal. So the tangent vector is orthogonal to the position vector if the vector function is of constant length. And a circle is a great example of this. Okay, so we refreshed our single variable differentiation techniques. Did we cover all of them? No, but they will all come up in different vector functions. We talked about how to write the equation of a tangent line now when we're given a vector function. We looked at our differentiation rules and how they really just carry over from single variable calculus. And we have three product rules though: scalar in a vector, vector dot a vector function, and vector function cross a vector function. And then we ended with this example, and also the unit tangent. Okay, unit tangent is an important vector that we defined. So we'll practice a bunch with this, get more comfortable, and then we'll keep moving.